All right, so this is a solution video for the practice exam for midterm number 2, and this is for version 2. And if you look at the video description below this video, you will see the timestamp for each problem. So if you click on the timestamp, you can jump to the corresponding problem. All right, and then now this is a question number 1, part A. So let f of x be x squared y minus 3y, and then compute the gradient of f evaluated at 1, 1. So here's the answer. So let's remember the gradient of f, or gradient of f of xy to be precise, is the vector where each component is the partial derivative. And then, so if you differentiate this with x, you get 2xy. And if you differentiate it with y, you get x squared minus 3. And then you have to evaluate this at 1, 1. So therefore, the gradient of f evaluated at 1, 1 is, you just plug in 1, 1 here, and you get 2, negative 2, actually. All right, so that's the answer. Okay, for part B, compute the directional derivative. Oops, so this is not xy. Evaluate 1, 1, sorry. Directional derivative of this f, the same f, in the direction of u, which is given this way, evaluated at 1, 1. Okay, so strictly speaking, you can actually check that the magnitude of u is indeed a 1, which means u is a unit vector. Indeed, this is 1 negative 1 over root 10 squared plus negative 3 over root 10 squared, and that's 1 over 10 plus 9 over 10, and that's indeed 10 over 10, 1. So indeed u is a unit vector, but you don't really have to write it down. You may just assume that this is a unit vector if the problem is given in this way. Anyhow, so let's just compute the directional derivative. Excuse me. And let's remember the directional derivative evaluated at, in this case, 1, 1, is the gradient of f evaluated at 1, 1. That's actually this from the previous part. Dot product with u. So that means 2, negative 2, dot negative 1 over root 10, negative 3 over root 10. Root 10. And if you work this out, you get negative 2 over root 10 plus 6 over root 10. And that gives you 4 over root 10. So that's the answer. Problem number 2, part A. Evaluate this double integral where B is the region given this way. So remember, this means x is from 1 to 2 and y is from negative 1 to 0. So it's a rectangular region. Although you don't have to write down the picture for this. Let me just write it down. So x is from 1 to 2, and then y is from 0 to negative 1. So it looks like this. Indeed, it's a square, actually. So this is our B. Anyhow, so this is the simplest case of double integral, dA. So you can just integrate each variable separately. So dx, and x is from 1 to 2, and y is from negative 1 to 0. And that is, so you integrate the inner integral first, and that gives you 1/2 x squared plus xy x is equal to 1, x is equal to 2, dy. And then this is simplified as you plug in 2 and 1, subtract, and then simplify. You are supposed to get 3/2 plus y dy. And then you just integrate it with y, you get 1/2 y squared, and evaluate from -1 to 0, and then you are supposed to get 1. Now, problem number 2, this is part B, sorry. Part B, use a chain rule to find partial z, partial t if z is xy and x is s plus t squared and y is s minus t. So remember the chain rule? So z is a function of x and y in this case. And then x and y, each of them is a function of s and t. And then you want to find a partial z, partial t. So you look at those, and there are 2 paths reaching t from z, namely this one and this path. And you label each edge by the corresponding partial derivative. And this here partial x, partial t, and partial y, partial t. And then multiply them and add all the paths. So by the chain rule, partial z, partial t is, first you look at this path, partial z, partial x times partial x, partial t, plus, now you look at this path, partial z, partial y, dot, partial y, partial t. So you compute each of those. Partial z, partial x is y, and then partial x, partial t is, so you differentiate this with t, you get 2t. And then now partial z, partial y, that's x times partial y, partial t, that's -1. And then you want to express everything in terms of s and t. So y is s minus t, dot 2t, plus x is s plus t squared, and then -1. And then if you simplify this, if you expand it and simplify everything, you are supposed to get -3t squared plus 2st -s. So that's the answer. Now, this is problem number 3. Let f of xy be this. Find all the critical values and classify them, meaning that find all critical values and then classify them means that just to determine if they give you a local maximum, local minimum, or a saddle point. So first, let's find all the critical values, critical points, and those are the points where both of the partial derivatives are 0. So let's just compute f sub x, and that is 2x plus 12y, and I'll compute f sub y, and that's 12x plus 36y squared. And then you want to find x and y so that both of them are 0. And the first one of those gives you x is equal to -6y. And the second one gives you, this is simplified as x plus 3y squared is equal to 0. Then now you can plug in this x to here, and then this gives you negative 6y plus 3y squared is equal to 0. Therefore, this gives you what? Therefore, we have y squared minus 2y is equal to 0. Namely, if you factor out y is equal to 0, so this gives you y is 0 or 2. And if y is equal to 0, since x is equal to negative 6y, let me just wait. Now, since x is equal to negative 6y, we have, if y is 0, you get 0. And if y is if y is 2, x is negative 12. So, therefore, 0, x 0, y 0, 0, 0, and negative 12, 2 give you the critical points. Those are, so to speak, the critical points. Critical points. Okay, then now, so that means each of those either gives you local maximum, local minimum, or a saddle point. You have to determine them. Like how? Well, by looking at second partial derivatives, namely by computing d of xy first. What's d of xy? This is partial f xx and xy, yx, and yy. And then compute the determinant. What is this? Well, first you compute f sub xx, so you differentiate this with x again, you get 2. And then now, to get this, you look at the same function and differentiate with y, you get 12. And then the middle guy is the same as, the third guy is the same as this one, so it's 12 again. Remember, fxy is the same as fyx. And then finally, you differentiate fy with y again, and then you get what? Well, 72y. And then if you multiply diagonally, subtract one from the other, you get 144y minus 144. Okay, and then we determine the value of d for each of those to check if it's a local maximum, local minimum, or a saddle point. Now, first let's take care of 0, 0. And 0, 0 is what? You just plug in 0, 0 here, then you get negative 144. Negative 144 is negative. So this automatically implies that 0, 0 is a saddle point. Saddle point. If d is negative, it's automatically a saddle point, and that's pretty much the end of the story. Then now, if you look at d of negative 12, 2, and then you just plug in negative 12, 2. But this is only a function of y, so you just plug in y is equal to 2. You get 144 times 2 minus 144. That's 144. And that is positive. So then now, if d is positive, then there are two possibilities. Either it's a local maximum or local minimum. To check that, we compute f sub xx evaluated at negative 12, 2. What's this? Well, actually, f sub xx appears here, and that's 2 no matter what. No matter what x and y are, it's always 2. And this is positive. So this second partial derivative is positive. This implies that, or actually to be precise, those two implies that this point, negative 12, 2, is a local minimum. All right, so that's the answer for this question. All right, this is problem number 4. Evaluate this double integral over the region where the region R is the region bounded by y is equal to root x and y is equal to x. So in this case, you have to sketch the region of integration. X and y is equal to root x. That's parabola like this. And this is y is equal to root x. And then now y is equal to x is a line. So this line is y is equal to x. All right, and then R is the region bounded by those. That means here. This is the region of our integration. And if you look at the point of intersection, point of intersection, that's 1 and 1. Okay, so let me move it down a little bit. Now we look at this double integral. Then remember, when you do double integral, you pick up one of the variables and then you fix one of the variables and you integrate with the other variable. And in this case, actually, it doesn't matter which one to choose, but let's choose x. And let's fix x. And for each fixed x, your y varies from this line, y is equal to x, to the parabola, y is equal to root x. So this one is written as, the given integral is written as 2xy. And you fix x and integrate with y, and y is from x to root x. And then, after you are done with this, you integrate with x. Now x is here to here. The smallest possible x is 0, and the largest possible x is 1. All right, so that's it. And then what you do is just calculate this. And if you look at the inner integral and integrate with y, you get xy squared. And you evaluate this from y is equal to x to y is equal to root x and dx. And that is equal to 0, 1. And then root x is x squared minus x cubed dx. And then of course this is computed as 1/3 x cubed minus 1/4 x to the power 4, 0, 1, and that is equal to 1/12. So that's the answer. All right, this is a problem number 5. Evaluate this double integral where the region R is given by this set notation. The set of all xy such that x squared plus y squared is between 1 and 4, and x is bigger than or equal to 0. Okay, then from this set notation, you have to visualize the region R. First of all, this part, this means we have seen something like this quite a few times actually. X squared plus y squared is 1, that's circle with radius 1. And the 4, that's circle with radius 2. And then it's in between, so that means it's between the circle with radius 1 and the circle with radius 2. And then x is bigger than or equal to 0. That means what does that mean? That means on the xy plane, you just look at only this part of xy plane. So if you combine those, the region of integration R actually looks like this. Y, x, and then circle with radius 1 and circle with radius 2 in the region where x is bigger than or equal to 0. So that means the region of integration is this part, 1 to -1, -2, negative 2. All right, and then what? Well, since the region of integration is like a part of a disk, we have to use polar coordinates. So by the polar coordinates, so we do x is equal to r cosine theta, y is equal to r sine theta, and then dA is r dr d theta. And then we have to find the limit, but since radius is between 1 and 2, r is between 1 and 2, then now for theta, what is theta? Theta is the angle measured from the x-axis. So this angle is theta, right? And I ask this question, in order for you to be inside this shaded region, your theta has to be what? Well, at most this much, pi half. So the upper limit is pi half. But what's the lower limit? Well, lower limit is less than 0. 0 means the x-axis, right? Theta 0. But you can go all the way up to the other side of the y-axis. So that means actually theta is from negative pi half to pi. So those are the limits for theta. And then also for polar coordinates, you often use x squared plus y squared is equal to r squared. And then all you have to do is just plug in those to here. And then what do you get? So therefore, the given double integral, this one is computed as, so x is r cosine theta, and then x squared plus y squared is r squared, and r is always positive, so you take the square root, that's just r. Well, maybe to be precise, r squared square root. And then dA is r dr d theta. And then the limits are r is from 1 to 2 and pi is from this. Okay, and then if you simplify this, if you simplify the integrand, pi over 2, 1, 2, and then how many r's do you have? 3. R cubed cosine theta and dr d theta. All right, and then this one is, by the way, here's a sort of shortcut for this. Well, maybe not shortcut, but here's one way to write it down. Cosine theta is viewed as a constant, right? With respect to the variable r, cosine theta is just a constant, so you can just take this out. And then moreover, after you take this out, and if you look at this part, this would be just a constant. That would just give you a number, right? So you can take out number outside of integral. So therefore, this is written as 1, 2, r cubed dr times negative pi over 2 dA cosine theta d theta. So you can just separate like this. Or if you didn't really understand what I did here, you may just compute step by step, doesn't matter. But in any case, this is written as 1/4 r to the power 4, and the r is evaluated from 1 to 2 times cos, if you're going to cosine, get sine theta, and then pi over 2, negative pi over 2. And if you work this out, you are supposed to get 15 over 2. So that's the answer. All right. So this is the last problem, problem number 6. Consider this double integral. Now, part A, sketch the region of this integration. So, to do this, you have to read off the region of integration by looking at the limits of integral. And then when you do this, essentially what you have to do first is to look at the first integral. And that is with respect to y. And then if you look at the limits, what's hidden is actually y is equal to x squared and y is equal to 4. And those are the two things that are hidden from the notation. Then now, y is equal to x squared is a parabola. Like this. Y is equal to x squared. And then y is equal to 4 is a line, horizontal line at, y is equal to 4. And then now, what this is saying is that for fixed x, your y value varies from the parabola to 4. So that means essentially it's inside this parabola, and then your x value is from 0 to 2, and indeed you can see that this is actually, this is 2. So the region of integration is this shaded region. This is y is equal to 4, and this is y is equal to x squared. So that's the answer. And now, part B, evaluate this integral by changing the order of integration, meaning that here, in this given form, the integral is with y first, and then x. And what you want to do is to switch the order of integration, namely you integrate with x first, and then y. And then for that, basically in this picture, the given integral is with respect to y first, namely you fix x and integrate with y vertically. And then now, this time you fix y, and for each fixed y, you integrate with x horizontally like this. Now, so that means for each fixed x, your y value is from what to what? I'm sorry, no, for the other way around. For each y, your x value is what to what? Where x value is from 0, y-axis is 0, to the parabola. And to get that, you have to solve it for x. X is equal to root y in the positive side. So that means x is from 0 to root y. And the integrand is 2x cosine y squared. 2x cosine y squared. And then you integrate with x. And then you integrate with y. And the y values are from 0 to 4. The smallest possible y value is 0. And the largest possible y value is 4. So you have this. So this is the integral you have to set up. And then all you have to do is just work this out. 0, 4. I forgot dy. And this is 0, 4. And then you integrate with x, you get x squared cosine y squared. This looks complicated, but it just stays there because it's treated like a constant. And then x is from 0 to root y and dy. And that is equal to 0, 4. And then now if you plug in here, you get y cosine y squared minus x is 0, so just a 0. So that means that's it. And then dy. Okay. And then here you have to do u substitution to compute the antiderivative of this. And then you will see 1/2 sine y squared. Oops. And then y is from 0 to 4. So like I said here, strictly speaking, you use u substitution. U is equal to y squared. And then if you work this out, you get 1/2 sine 16. So that's the final answer. All right, so this is the end of the solution video for this.